Have you ever wondered where and how your daily portion of leafy vegetables are produced? I think we can all agree that leafy greens are an essential part of our healthy diet, but beyond their nutritional value, you might wonder, are those produced in a sustainable way? And what about food safety? Let's talk about an alternative way of producing leafy vegetables other than outdoor soil-based agriculture. Topic of today: aquaponic farming in an urban environment from a food safety perspective. Our agri-food systems are under pressure, impacted by drivers of change like climate change, the increasing population, urbanization, and depletion of natural resources. Therefore, international organizations like the Food and Agriculture Organization of the United Nations and the European Commission call for action to transform our food system. Transformation to more efficient, inclusive, resilient, and sustainable agri-food systems. One way to address those challenges is looking for an alternative production system, and we see that conventional agricultural systems are transforming towards more controlled environments. These systems benefit from the stable environment in terms of light, temperature, and humidity, which gives better yields, uses less available land when, for example, producing plants vertically, and uses resources more efficiently, for example, by introducing circular principles, reusing water and nutrients rather than relying on constant flow of external inputs. An example of such a system is the aquaponic farm we studied within the urban environment. But first, what is aquaponics? In simple terms, aquaponics combines aquaculture, here fish production, with horticulture, the production of leafy vegetables. Fish production leads to nutrient-rich wastewater, which is used as irrigation water for the leafy vegetables. Setting up and operating such systems requires substantial knowledge and presents several technological challenges. But fortunately, a growing body of research focuses on system design and operational parameters. But when transforming food systems to achieve circularity and sustainability goals, the recognition of food safety from design onwards is very important, to not only provide good, nutritious food for all, but also safe food for all. And not much research is out there on such newer, urban, circular systems like aquaponics in relation to food safety. And we already know very well what the risks are in the fresh produce production chain, and appropriate measures and good practices are out there to produce safely. But in aquaponics, there are some extra layers impacting food safety. It's an indoor, controlled environment with warm and humid conditions. It's a circular system combining animal and plant-based production, and it's production in an urban environment, which can all impact food safety. The limited research that is out there on aquaponics and food safety is performed in small lab-scale systems or highly controlled pilot scales. All this research is valuable, but there's a need for some upscaling to real-world examples. Therefore, we performed a microbial assessment of an aquaponic farm to gain insight in the microbiological safety of a commercial urban aquaponic farm. We wanted to understand the microbiological quality and safety of basil grown in the aquaponic system. We wanted to identify potential routes for introduction and spreading of foodborne pathogens throughout the system. And we wanted to evaluate the current system design, irrigation practices, water quality management in light of food safety. In the system, several water sources are used and mixed for irrigation. These include well water coming from an on-site borehole, rainwater collected from the greenhouse roofs, and fish water, which is the aquaculture process water from the recirculating aquaculture unit. And then we have drain water or spent irrigation water from the herbs greenhouse itself where the basil is grown. These water streams are mixed, recirculated, and reused during production of approximately 2 months after cleaning and disinfection. We collected water samples from each water source before and after UV or biofiltration treatments from the irrigation tank itself and the point of irrigation. And here you can see the results of our microbiological analysis. I showed 3 microbiological parameters: the total bacterial count. More bacteria does not equalize good or bad in terms of food safety. Then we have E. coli as indicator for fecal contamination and Salmonella as a foodborne pathogen. We can see a low bacterial load in well water, rainwater and fish water comparable to the range we would expect in potable water. Not to say that potable water should be used in the system, but as comparison of microbiological loads. Regarding fecal contamination, we see that E. coli can arise from roof-harvested rainwater in low concentrations. And considering food safety, some Salmonella bacteria might end up in the system coming from the fish water or rainwater. These water streams are then mixed and used as irrigation water for the basil plants. We followed 6 cycles of basil growth from seed to mature plant. Samples were taken in 3 time points for every batch, every 2 weeks related to the stage in the growth cycle of basil. So seeds, sprouted seeds, small basil plants at the end of the overhead irrigation stage when irrigation switches to subsurface tide table irrigation, and at the end of the production cycle. On top of the slide, I'm showing the results of the seeds and basil leaves, and at the bottom of this, the substrate over time. The substrate quality is of high importance for food safety. Here, Salmonella was present in the beginning, but seems to be outcompeted over time due to the high bacterial loads of approximately 7 to 8 logs per gram. Also, high levels of E. coli were present in the substrate, but we found no indication of fecal contamination nor food safety issues on the edible plant portion. So in our analysis, the basil was always safe to consume. But I also showed that pathogen introduction from, for example, the peat moss substrate and the rainwater is possible. And if pathogens are introduced, due to the complex and circular nature of the system, there might be a risk of spreading throughout the system. And Salmonella on basil is still relevant, as shown by this outbreak of Salmonella on basil in the United States. Therefore, we think it's important to create awareness on food safety and generate knowledge. As aquaponic food producer, you have to know what you are doing, follow trainings, train your people, and embed food safety in your organization, its culture. You also have to understand your water streams, what risks are related to them, and how to appropriately treat, sanitize, and use them. Because water can introduce pathogens, but can also act as a vehicle for pathogen spread. We all know that bacteria and pathogens are not visible, but you have to be aware of their presence or for pathogens' potential presence and think about effective ways to prevent their introduction or eliminate them once introduced. I want to conclude with mentioning that our goal with food safety research on alternative, circular and more sustainable ways of food production is not at all to link a negative story to those systems, but to improve the system, setting up good practices and guidelines to mitigate the introduction and persistence of foodborne pathogens. There's a need for food safety knowledge, but also interdisciplinary plant-fish pathogen knowledge to truly understand aquaponics in terms of food safety. We want to create awareness that food safety is important when transforming food systems to achieve sustainability goals, and this all to improve aquaponics and to provide sustainable food, your sustainable portion of daily leafy greens that is not only good, nutritious, sustainable, but also safe. If you want to explore this topic in more detail, the full research study titled Microbiological Hygiene and Food Safety Assessment of Urban Aquaponic Farming has been published in the International Journal of Food Microbiology. The article, including all references, is available for open access.